So let's talk about buoyant forces. It turns out that any object that is in a fluid is going to experience a buoyant force. Now, ultimately, that buoyant force, if I think about a big old pool or some sort of container of water, and I toss an object in here, depending upon the density of the object could potentially sink or float. I'm going to draw floating for just a second. The bottom of the object down here, the pressure it experiences is larger than the pressure up here, because the pressure at the top is the atmospheric pressure, but the pressure at the bottom is higher because we're at a depth D, we're down displacing some of the fluid. So the difference in pressure between top and bottom ultimately is why we're having a buoyant force. Archimedes is attributed to it's called Archimedes' principle. The buoyant force an object experiences is equal to the weight of the fluid displaced. So in my picture, my little green box, that bottom part of the box that I've scribbled out is now located in a region of space where water used to be. And so what this Archimedes principle is telling me is there is an upward buoyancy force. I'm going to just call it F sub B. That upward buoyancy force that this block experiences will equal the weight of the fluid displaced by the block. That means mg of the fluid that was displaced. All right, now there's going to be two ways to look at problems. If I look at just this block, there's an upward buoyancy force, but I know the block is not actually accelerating upwards. The block is also experiencing its own mg. So mg of the block. In terms of Newton's second law, if this block is floating, its acceleration is 0. So that buoyant force upwards must equal mg, the weight of the block itself, downwards. So that's just from previous sections. If there's no acceleration, the net force needs to be 0. So the upward force will equal the downward force. Okay. So this is the byproduct of just floating. And looking at Newton's second law, I'm going to call this m sub o for the object that's floating. Of the object that is floating. All right, now coming back to Archimedes' principle, the buoyant force on any object. This is true whether the object is floating or not. Any object that is now currently where fluid was will experience a buoyant force. And that buoyant force will always equal the weight of the fluid displaced. I'm going to write this mass sub F for the fluid, and then G. All right. So, mass of the fluid. Coming back to my picture, I essentially need to know the mass of that much water, or whatever fluid it happens to be. It doesn't even have to be water. I need the mass of that portion. Now, we don't typically talk about the mass of our fluids. We talk about density. So the density is going to be mass per volume, which means we can say the mass of the fluid is equal to the density of the fluid times the volume. I'm going to call this V sub D, the volume displaced. The amount of fluid that had to move to let that portion of the block be there. So in place of mass of the fluid, I'm putting density of the fluid, volume displaced, and then we need G to make this our force. So the force of buoyancy depends upon the density of the fluid. It depends upon the volume of the fluid that is now moved out of the way, and it depends upon G. I'm going to write this also as Vn. So density of the fluid, Vn times G. The amount of fluid that displaces is equal to the volume of the object in the fluid. That's what I mean by Vn. My whole block is not physically in the fluid, it's only a portion of it. And that's what I mean by Vn, the V that's actually in the water. So for example, if we think about icebergs, big, huge icebergs near the poles, how much of an iceberg is submerged in the ocean? So we have this ocean, we have this huge iceberg, really weird shape. Here's my iceberg. If we think about Vn, volume displaced, it's this portion of the iceberg that is in the water. So the buoyancy force, based off of just this equation right here, is going to be the density of the water, because that is the fluid. So seawater specifically, they're out in the ocean. So the density of the fluid, the volume in, times G. Now, this by itself is not enough. But if I come and think about net force, I know the buoyancy force upwards is balancing out with the mass of this iceberg times G. They're floating out in the ocean. So that buoyant force is lifting it up while the force of gravity is pulling down. Well, the mass of the ice is going to equal the density of the ice times the volume total of the iceberg. So I can say this is density of the ice, total volume of the iceberg times G. By equating these two, I can solve for Vn over V total. This isn't going to give me an actual volume, but it's going to give me a percentage. So what percentage of the total volume resides in the water? I'm left with density of ice on the right, and I'll bring over the density of seawater. The G's cancel when we equate those two. So test notes. Ice has a density of 920 kilograms per meter cubed. Seawater has a density of 1030 kilograms per meter cubed. I get 0.89. This tells me that 89% of an iceberg is submerged, is underwater. That means 11% of the iceberg is above water. We only see approximately 11% of an iceberg. Well, if we ever get to go see one. I have not been north or south far enough to see one in person, though I hope to someday. It turns out anything that is floating, anything that is floating will end up with the buoyant force, so the density of the fluid, density of the fluid, volume N times G. So this basic equation for buoyant force, this is always true, but this buoyant force must equal the mg of the object itself for any object that floats in a fluid. And we can always write the mass of the object as the density that the object, the material it is made of. So the density of the object, the volume of the object as a whole, times G. So our fundamental equation for buoyancy is density of the fluid, volume N times G. But if an object is floating, Newton's second law tells us that buoyancy force needs to equal the weight of the object as well. Any object whose density is less than the density of the fluid will float. If the object has a density that happens to be the same as the density of the fluid, the object has what we call neutral buoyancy. So it's still floating, but it floats completely submerged. So if we had our container that has water, the block would just float completely submerged in here. It wouldn't have any portion completely out of the water, nor would it completely sink to the bottom. if the density of the object is greater than the density of the fluid, the object sinks. So if I have, say, a piece of iron, a block of iron, I drop it in some water, it's going to sink to the bottom. It will experience a buoyant force. And this buoyant force will equal the density of the fluid, the volume in, meaning the volume of this block. Since the block is completely submerged, we could just say V sub O, meaning the volume of the block itself, the volume of the object. So that is our fundamental equation for buoyancy forces. But to relate that to weight of the block, for example, we know the block itself will have the force of gravity, its own weight. But this time we would also have a normal force because it's on a surface now. It's on the bottom of the container. And so to balance out for Newton's second law, there's no acceleration because this block is sitting at the bottom of the container. We would need both the normal force and the buoyant force upwards. Those two are acting upwards together to counteract the weight of the object. So mass of the object times g. So we do need, we're going to be revisiting this whole Newton's second law business. Net force, we're going to have our objects be in equilibrium, not accelerating, but we will still need to recognize all the forces acting on the object. And then the new piece is that buoyancy forces, just the fundamental equation for them, depends upon the density of the fluid, the volume of the object that's physically submerged in the fluid, so the volume displaced, and g. So I'll go through a couple examples so that you can see how to apply this in a couple different situations.